Welcome to our Pathfinder program on Kawasaki engine fuel systems, now in wide use on John Deere equipment. There are three basic areas of information that we will cover on these systems: principles of operation, fuel system adjustments, and diagnostics. There are also individual topics in each of these areas, each presented in short segments, which allow you to stop the program at a number of different points for review or just for a break. Let's begin. Fuel systems on Kawasaki engines have several different elements which must work together to provide the best engine performance. They include air supply, fuel supply, carburetor, and governor. We'll start with the air supply. Air is drawn into the blower housing through this rotating screen. Contour blades built into it chop up any grass or debris that enter and discharge it around the edges. Keeping the screen open is very important, since it provides the airflow for both the cooling of the engine and for the supply needed by the carburetor. Operating an engine in extremely dusty conditions may require that the engine shroud be removed periodically for cleaning of the engine fins and air passages. After the air leaves the blower screen, it travels under the engine shroud and enters the filter housing. Since it's moving at a fairly high rate of speed around the curve of the housing, centrifugal force throws the larger particles of debris and dust out the side. The remaining air, which is relatively clean, enters the air filter. Keep in mind that the volume and velocity of the air is controlled by the design of the housing. So if anything changes the path of the air, it will affect the operation of the carburetor. This includes dirt clogging the air filter. The filter assembly is made up of a foam-type pre-filter and the filter itself. To clean the pre-filter, remove it from the filter element and clean it in a non-flammable solvent. After it's dry, pour a few drops of oil on it. Wring it out and reinstall it. The oil helps it trap dust more effectively. The primary filter should also be inspected and replaced if necessary. After leaving the filter assembly, the clean air then enters the carburetor. We'll have more on our carburetors in a few moments. First, however, let's look at the fuel system. There are two basic ways to move the fuel from the tank to the carburetor. If the fuel tank is positioned higher than the carburetor, gravity feed is used. But if the tank is lower than the carburetor, a fuel pump is required. In some instances, a fuel pump and gravity are both used in combination. Fuel tanks may have a screen on the fuel line pickup to prevent debris from getting into the system. And inline filters like this are also common. Most systems will feature some type of fuel shutoff valve. It can be used during long-term storage, during short-term draining of the fuel system, and also to prevent fuel from getting into the engine during transport. If a fuel pump is needed, Kawasaki engines commonly use a diaphragm pump that is driven by vacuum pulses received from the engine. The pump will either be mounted separately or it may be built into the carburetor itself. That's a brief overview of the air and fuel supply systems. Now, let's look at our carburetors in detail. There are two basic types of Kawasaki carburetors on our equipment: float and pulse. The float type receives its fuel through a line from the fuel pump or the tank, while the pulse carburetor relies on a diaphragm pump built into the body of the carburetor itself. The carburetor is mounted on the engine with stud bolts, and in most cases, there will be an insulator piece with gaskets installed between the carburetor and the engine block to reduce heat transfer. Now, let's look at the pulse carburetor in detail. You will generally find them used in small engine applications, such as lawn edgers. It has a manually operated choke and a throttle valve that rotates with throttle position or the position of the governor control rod. There are two adjustment screws, one to adjust idle speed and the other to adjust the volume of the idle fuel-air mixture. The fuel pump section has a long fuel intake pipe with a strainer at the end to filter foreign particles out of the fuel as it is drawn out of the tank. Pump suction is created by a flexible diaphragm installed between the upper and lower body parts with a gasket. Let's take a few moments to see how it works using this animated drawing. An air passage, or pulse port, connects the top of the diaphragm chamber with the intake manifold side of the carburetor. When the piston is on its downward stroke, it creates a vacuum above the diaphragm, which then flexes upward, creating a suction effect below it. The fuel is drawn up the intake pipe, filling the chamber. When the piston is on its upward stroke, there is a decrease in the vacuum above the diaphragm. This allows the spring to force the diaphragm down. The inlet check valve closes and the outlet check valve opens, and fuel is pumped into the fuel chamber, also located in the lower body of the carburetor. Here's the entire cycle. The fuel chamber reservoir is designed to provide a constant fuel level by simply allowing excess fuel pumped in to drain back to the fuel tank. That's all there is to it. Now, let's look at the principles of operation of the pulse carburetor. The pulse carburetor has three basic circuits or modes of operation: the start circuit, idle circuit, and main circuit. The start, or choke circuit, is designed to provide a very fuel-rich mixture for easy startup. The idle circuit, sometimes called the pilot, provides fuel to operate the engine under very slow or no-load conditions. The main circuit functions when the engine is operating at partial to full throttle. We'll begin with the main circuit and explain how the primary components work. There are two basic controls on the flow of air through the barrel of the carburetor: the choke valve and the throttle valve. When the main circuit is in operation, the choke valve is completely open, and the throttle valve is either partially or completely open. After the air passes the choke, it enters the venturi, which compresses the air and increases its speed. The pressure then drops as the barrel becomes larger again, creating a partial vacuum. At the same time, part of the air enters the main air jet and is channeled down to the main air bleed. We'll show you what happens with it in a moment. First, let's look at the fuel side. At the heart of the carburetor is the main fuel nozzle. The main fuel jet is connected to the bottom of the nozzle, below the surface of the fuel. The main jet meters the fuel that is drawn up into the nozzle during operation. Now, let's see how these components work together to create a fuel-air mixture for the engine. We mentioned earlier that the air rushing through the venturi created a partial vacuum in this area. As a result, the air pressure is lower in the barrel of the carburetor than it is in the fuel chamber. This pushes fuel up through the main fuel jet and into the main nozzle. At the same time, air from the main jet is forced through the air bleed holes in the main nozzle, creating a bubbly mixture of air and fuel. This light mixture is lifted up the tube, where it is hit by the high-velocity air coming through the venturi. This atomizes the mixture, resulting in a very even and fine mist of fuel and air for the engine. Here's an important point to keep in mind. Both the main air jet and the main fuel jet are fixed. This means you cannot adjust either the fuel flow or the air flow. That's how the main, or high-speed circuit works on this carburetor. Next, let's take a look at the idle circuit, why it is needed and how it works. The reason a separate idle circuit is needed is that when the throttle valve is only slightly open and the engine is turning over very slowly, there isn't enough airflow through the carburetor to pull fuel up through the main nozzle. Therefore, to keep the engine supplied with fuel, a second, smaller tube is connected to the lower portion of the main nozzle to supply fuel for the idle circuit operation. A restriction is designed into the tube to serve as an idle jet. Again, as with the main fuel jet, there is no adjustment possible. Air for the idle circuit is drawn through a separate tube built into the carburetor wall with a fixed air jet inside it, also not adjustable. Let's see how it works. When the engine idles, the intake stroke will create a low pressure condition which draws air in through the idle air jet. This air, passing over the top of the idle fuel tube, creates enough suction to draw fuel up through the tube. The air and fuel mixture is then routed around and actually bypasses the throttle completely before entering the barrel through a pilot outlet. As we said, both the idle air and fuel jets are fixed, so individual adjustments cannot be made. However, the idle circuit does have a needle valve at the pilot outlet that can be used to adjust the amount of the fuel-air mixture entering the carburetor. In addition, the carburetor has an idle stop screw used for setting the minimum speed. The final circuit we will examine on the pulse carburetor is the start or choke circuit. The choke is operated by moving a slide on the top of the carburetor body. The purpose of the choke valve is to shut off nearly all the airflow into the carburetor. When this happens, the vacuum created by the intake stroke of the engine pulls fuel up through the main jet, but gets very little air. The result is a very rich fuel-air mixture, which enables easier starting. That wraps up our look at the principles of operation of pulse carburetors. We'll cover practical hands-on adjustments and diagnostics later. Now, we are going to examine the principles of operation of the float-type carburetor used on Kawasaki engines. The float design is usually installed on larger equipment, such as lawn tractors. As you now know, the pulse type has a diaphragm fuel pump built into the lower body of the carburetor. That's not the case with the float type. If the system needs a pump in addition to gravity feed, it will be mounted separately and will send the fuel to the carburetor through a fuel line. The principles of operation of the fuel pump are the same as those described earlier. A flexible diaphragm is driven by vacuum pulses received from the engine. We'll have more on the operation of pulse pumps during diagnostics later in the course. Let's begin with the float bowl bolted to the bottom of the carburetor. The screw and spring are not used for any type of adjustment. What they do is provide a quick and easy way to see whether there is any fuel in the bowl. And it also can be used as a drain for seasonal storage. The float name for the carburetor comes from the plastic float used to maintain the level of fuel in the float bowl at a more or less constant level. Proper operation of this float is critical, since atmospheric pressure on the fuel in the bowl, coupled with precise carburetor design, provide for transfer and atomization of fuel. The float maintains the proper level through a needle valve attached to it. When the level goes up, the float pivots upward and the needle valve seats. When the level drops, the float drops down and the needle valve opens, admitting more fuel from the tank or fuel pump. On some Kawasaki carburetors, usually those with a black-colored float, the float level may be adjusted by bending this metal clip that attaches to the needle valve. Some carburetors have white floats, which cannot be adjusted because the tang that positions the needle valve is made of plastic. Float-type carburetors have two adjustments. There's a screw to adjust the idle speed and another to set the volume of the fuel-air mixture. The fuel and air jets are not adjustable. The float carburetor has a manually operated choke and a throttle valve that rotates with throttle or governor rod position. Some models also feature a fuel shutoff solenoid to prevent afterbang, the detonation of unused fuel in the muffler that happens after the ignition is turned off and the engine is winding down. When the ignition is on, the solenoid plunger retracts, allowing fuel to enter the main nozzle. But when the ignition is turned off, the plunger extends, blocking the flow of fuel to the main nozzle. Now that we've covered the basic elements of the float carburetor, let's take a look at the principles of operation of the main circuit, idle circuit, and start circuit. As you will soon see, they are virtually identical to those of the pulse, but there are differences that we will point out to you. First, the main circuit. The main circuit functions when the engine is operating at partial to full throttle. The choke is all the way open, and the throttle valve is wide open or nearly wide open. In this condition, a high volume of air flows very rapidly into the throat of the carburetor, picks up speed as it is funneled through the venturi, then drops in pressure as it passes over the top of the main nozzle. Since the air pressure is lower above the main nozzle than it is in the float bowl, fuel is drawn up through the main fuel jet. At the same time, part of the incoming air enters the main air jet and bubbles through the air bleed holes in the main nozzle. This mixture of air and fuel is light enough that it is drawn up the main nozzle by the lower pressure above it. The main airflow rushing across the top of the main nozzle picks up the fuel-air mixture and further atomizes it in the airstream. The mixture is now highly combustible as it leaves the carburetor. The main air jet is built into the wall of the carburetor, and no adjustment can be made to it. Some, however, are replaceable. The main fuel jet cannot be adjusted either, but it can be removed from the nozzle tube for cleaning or replacement. The size of the orifice in the main jet is determined by the engine and its application. For example, if the engine will be operating in a high-altitude location, it may be necessary to change the jet to a smaller size for more efficient operation. Calibrated jets are available for altitude adjustment. Now that we've covered the main circuit, let's take a look at the idle or pilot circuit, also very similar to its counterpart in the pulse carburetor. The idle circuit provides fuel and air to operate the engine under very slow or no load conditions. The choke is wide open, and the throttle valve will be closed or nearly closed. As a result, the airflow through the venturi is not fast enough to draw fuel up through the main nozzle. The slight vacuum created by the intake stroke of the engine is sufficient to draw fuel through the main fuel jet and up a small tube to the pilot jet. Here it mixes with a small amount of incoming air from the pilot air jet. The mixture of fuel and air then enters the barrel of the carburetor at the pilot outlet behind the throttle valve. The float carburetor idle circuit also features one or more transition holes, located here. The transition holes allow more fuel to enter the barrel as the throttle valve begins to open. The purpose of these holes is to smooth the transition between the idle and main circuit as the throttle is opened and the engine accelerates. Then, once the throttle is open, airflow past the main nozzle is fast enough to activate the main circuit, and the idle circuit is no longer needed, even though it does continue to operate. As with the pulse, the pilot air and pilot fuel jets are not adjustable, and the pilot needle valve is used to adjust only the volume of the fuel-air mixture entering the carburetor, not the ratio of fuel to air. The pilot jet must not be installed too tightly, only finger tight. Over-tightening can distort the intended position and will affect the fuel and air mixture. Some float carburetors come equipped with a screw and clip to lock the position of the pilot jet in place after adjustment. This is done to properly locate the pilot jet with respect to the air passage. That's a basic look at the idle circuit on the float carburetor and how it functions. Now let's examine the start or choke circuit. The start circuit is designed to provide the engine with a very fuel-rich mixture to aid in easy starting of the engine. When the choke is closed, most of the airflow into the carburetor is restricted. Some designs have one or more holes in the plate, and others only partially close off the air passage. In any case, no matter what the design, the choke plate cuts down on intake air, while the partial vacuum created by the engine draws fuel up through both the main and idle circuit. The fuel mixes with a small amount of air at both the main nozzle and pilot jet, and the fuel-rich mixture enters the engine. That wraps up our look at the float carburetor from Kawasaki. We'll be back with governors in a few moments.